Okay, so in the last video, I talked about the bias in the variance of beta 1 or any beta coefficient that could be introduced if you include an irrelevant variable in the model. In this video, I'm going to keep talking about the variance, and in particular, I'm going to talk about the sampling variance that we get from OLS estimates. And one thing to note here is that we do not know the population variance, so we have to estimate it from the sampling variance. And we know that we can estimate this by using this formula. We can use our estimated model to estimate these errors. And from this, we can estimate sigma squared. So remember, whenever we put a hat on a variable, it means it's an estimate. So our sigma squared estimated for this is equal to, we add all the errors and take the square of them, I to n, and then divide it by n minus k minus 1. Now this denominator, it is called degrees of freedom. And here, n is the number of observations in our data. K is the number of, actually both is number of parameters in the model. And that is, since here we are estimating k plus 1. This is the plus 1 coefficient. So we are estimating these many coefficients. So if we do that, we get degrees of freedom. And the idea of degrees of freedom is as follows. Let's say we have just one observation in the data. So our degrees of freedom, if we want to estimate a model like this model with only one variable, here k is 1, so n minus 2. So our degrees of freedom is minus 1. So seems like we cannot estimate this model. Why? Because essentially we can draw a line like this, and like this. And we do not know which line is a better one. So if we have two observations for this data, then our degrees of freedom is 0, right? So including here a small, so see, this line will go through these points and we'll have a perfect fit. So ideally, what we want is that n is sufficiently larger than k. That is, we have some degrees of freedom in order to estimate a model. For example, in a model like this, we have n sufficiently larger than k. K is 2 here, and we can estimate a line like this in this case. Therefore, it is important that we take care of these degrees of freedom in our model. So this is the estimated sampling variance. If we take the positive square root of this, it is called standard error of the regression. And note that this standard error, it can decrease or increase when another independent variable is added to a regression model. And this happens because we know that the residual sum of square is going to fall when another variable is included in the model. But the degrees of freedom also falls by 1. And because residual sum of square is in the numerator and degrees of freedom is in the denominator, we cannot tell beforehand which effect will dominate. So we do not know whether this effect is going to be increase the variance or decrease the variance. So far we talked about 5 assumptions of OLS. The first one was about the linearity of these parameters. And the next one was that the sample is picked up at random. And the third was there is no perfect collinearity in between those variables. And the fourth one was zero conditional mean of this error term. And the fifth one, which is more important in this case, is the assumption of heteroscedasticity. That is, that the variance doesn't depend on either of these x values. So if this assumption is not met, then this OLS estimate of these variance will be biased. Hence, before we do anything, we have to make sure that our data is homoscedastic in order to make plausible interpretations of these beta coefficients, as we will see in the next chapter when this variance is going to play a huge role. All right, I'll see you in the next video. Bye-bye.